Okay, your assessment was based on some of these questions. I'm going to go through a few of them now. Looking at this first paragraph here, we've got some words from the box to pick from. It says the current through an ohmic conductor is directly proportional to the something, and here's our word across the component. So that gives me a clue that this word here is potential difference. We know the current is directly proportional to the potential difference, the voltage, provided that the key fact about ohmic conductors, we need a constant temperature. Here we've got one of the graphs from our component graph section. We're seeing the relationship between potential difference in volts and the current in amps, and the command word in this question is explain. And we're talking about how the resistance of the lamp changes as the potential difference across it increases. So if you think what resistance means how easy is it to push current through a conductor. So if the resistance goes up, then it gets more difficult for the potential difference to push a current through a conductor. So we can say for a bigger resistance and the same potential difference, you'd get less current, which we represent with the letter I. Or we could say when the resistance is bigger, you need a bigger voltage to push the same current. Our explanation for the lamp needs to include the fact that temperature isn't staying constant. So because the bigger potential difference that you can see on this axis is making a bigger current, the bigger current causes the filament in the lamp to get hotter, and as the wire gets hotter, the atoms in the wire are bouncing around with more energy, and this makes it harder for the electrons to flow through the filament of the lamp. So as the bigger current flows due to the larger potential difference, the temperature gets bigger, and because the temperature gets bigger, the resistance also goes up. And we can tell that from this graph because the gradient is getting flatter and flatter, which means it's harder and harder for the potential difference to push current through the conductor. Okay, this question trips a lot of you up in the exam. We've got a light dependent resistor in series with a 2000 ohm resistor connected to a 12 volt battery. So we've just got one series loop here. There are two wires connected across the LDR which are going to another circuit. So this is going to connect to a parallel circuit over here, but the question is about this series circuit. The light intensity decreases. What happens to the potential difference across the LDR and the current in the LDR? As the light intensity goes down, the current will go down and the potential difference will go up. Now part E, a calculation, looks trickier than it is, but look at what we know here. So we've got 12 volts in the battery, and we know that there's 4 volts across the LDR. Tells you in the question. So from that, we need to deduce that there'd be 8 volts across this resistor. Now this is a series circuit, so the current is the same everywhere. And so if I need 8 volts to push the same current through a 2000 ohm resistor here, 4 volts is half the potential difference, so it must be twice as easy to push the current through, so the resistance of the LDR would be 1000 ohms. Okay, let's maybe go through that again. We're saying that this voltage here is 8 volts because the question tells you that this is 4 volts, and 8 plus 4 equal 12. The voltage here has to be bigger because this resistance is bigger than this resistor. And look at the ratio of the voltages. If I've got half the volts to push the same current, because this is a series loop, so the same current everywhere, then this resistor must be half the resistance. Calculate the current through the LDR when the resistance of the LDR is 5,000 ohms and give your answer to two significant figures. Now we've just said that the current is the same in the whole circuit. So to answer this question here, we know that the LDR is 5,000 ohms. We know that the total resistance in the circuit is the sum of the individual resistances. So the total resistance is going to be 7,000 ohms. We know that the potential difference across both resistors, so if I put a voltmeter across here, across both, it would be reading 12 volts, the same as the battery, and we know that V equals IR. Rearranging that to find I, the current, we get the volts, 12 volts, divided by the resistance, 7,000, and that gives me an answer of 1.71 times 10 to the minus 3. Okay, this was another of your questions. We know what quantity the ammeter measures. Most people got that right. Ammeters measure the current. Notice it's connected in series. The current in the circuit, let's underline these values, 3.5 milliamps and the potential difference of 4.2 volts. And I need to calculate, command word, the resistance. So I'm looking for the equation that links these three things. I've got my V equals IR equation. Rearranged, the resistance is the potential difference divided by the current. I've got a potential difference of 4.2. And I've got a current of 3.5 milliamps. Okay? 3.5 milliamps is 3.5 thousandths of an amp, or 3.5 times 10 to the minus 3. Milli is a thousandth. And if we put that into our calculator, we get an answer of 1200 ohms. Part C is asking you to calculate the charge, command word, what I want to know, time, current. I'm going to use my charge equals current times time equation. I know the current is 3.5 milliamps. I know I need to change that into amps, so I'm going to do times 10 to the minus 3. And I need to multiply that by the time, which is 5 minutes, but I must have my time in seconds. So 5 minutes times 60, 300 seconds. That's going to give me an answer of 1.05 coulombs. Explain why the potential difference across the thermistor changes as the temperature in the house decreases. Now, lots of people got this the wrong way around. The resistance of the thermistor is bigger when the temperature goes down. So as the temperature falls, the resistance gets bigger, which means that the potential difference will have to go up. Okay? Why does the potential difference change? Because the resistance of the thermistor gets higher as the temperature falls, so the potential difference will get bigger. Now there's going to be 2 more questions for you to have a go at as a follow-up to this assessment. Look at this diagram here. We've got a power supply, a battery, current flowing. We've got a value for the current. We've got a voltmeter which is connected in parallel across this thermistor, and the thermistor is sitting in some water that's being warmed up. We should recall the diagram for a thermistor and be able to draw it. And then we've got some maths to do, looking at some data in figure 1. So I'm going back to figure 1. I've got some values here. I know the temperature is 20. I know the volts. I know the amps. I can use my Ohm's law equation, V equals IR, to calculate the resistance. Have a go at that now. Okay, when you've got these questions about graphs, we're being asked here to sketch a graph. Sketch just means showing the shape, but we don't need to put any values. So think what we know about thermistors. We need to remember the key fact that at higher temperatures, the resistance is lower. So I'm going to have a point down here somewhere. And at lower temperatures, the resistance is higher. There's going to be a point up here. Now, most graphs in science where one thing gets bigger and something gets smaller will follow the inverse proportionality shaped graph. And the inverse proportionality shaped graph is going to show a value going from a high to a low in a smooth curve. Have a go at interpreting the results to answer these next few questions. Look quickly at part D. A student plans to investigate how the resistance of a light-dependent resistor changes with light intensity. A student starts with the apparatus shown in figure 2 but makes 3 changes to the apparatus. One of the changes the student makes is to replace the thermistor with an LDR. Describe what other change the student would make to the apparatus. So if we're thinking here, what we need to be doing is showing that we understand that we're no longer changing the temperature with a Bunsen burner and some hot water, but we need some apparatus to be able to change the light. So either a lamp, and then we need to sense the amount of light, so we're going to need some sort of light sensor or measurement device for the light as well. Think of a sensible answer to this question. Finally, the last question is quite challenging. You need to use values derived from the graph. Have a go at this question, and we'll go through the answers at the end.